Okay, so good afternoon everyone. We will continue our discussion on this logic clocking. Okay. So, before the break I talked about this logic clocking concept, that you have this circuit, the circuit is locked with additional keys, right. So, if you have this additional key, this is the K1 and K2 is the key. So, whenever you give the correct value of the key, this circuit is equivalent to this circuit. Okay. So, this is your original circuit, you want to hide this information of the circuit, right. And if you give any other value, say 1 1 1 0 and all, the output will be corrupted. You may not have 100% corruptibility, in the sense that it is not that all possible input output will be wrong, but 70%, 80% cases if it is giving wrong output, it is good enough, right. So, that is the entire objective of logic clocking, okay. And this actually can give protection against all those counterfeiting, because even if you build this for counterfeit chip, you will not be able to use it because you do not have the keys, right. You can actually give protection against hardware trojan, because you do not know the functionality, you do not know where to insert the trojan, right, because you do not know what is the rare event and all, even if you know, but you are not able to use it, right. So, it will give you against the protection against this hardware trojan. Reverse engineering is basically you get back this from this layout, the package you get the design, but you will get the locked design, right. So, the same story, that you have the netlist, but you will not able to use it. Okay. And so effectively the logic clocking is something, is a technique that can give protection against all kind of the threats that we have in the IC supply chain. Okay. So, this is something the introduction on HLS in the logic clocking, sorry. So, so this example I think motivates you and give you the concept, right. So, now if you look into here, I basically lock something here, I lock something of this operation effectively, and I lock this condition. Okay. So, this is what exactly I have done, and I got this locked behavior, right. And then I have shown you that if you give wrong key, you will get not the desired results. Okay. So, now what I am going to talk in this class is on logic clocking at higher abstraction level. What do you mean by higher abstraction level? Is your C, C++ code or maybe the RTL design. Okay. So, this is the higher abstraction level. Most of the logic logging work you will see on the gate level design, which I will talk in today only, but I will start with the higher abstraction level, because that give you more visibility, in the sense you will more relate the changes that I am going to do. Okay. So, and why we should do in the locking at the higher abstraction level, because I mentioned that even the EDA tool that you are going to use, they can also kind of take the insight of your design, right. So, they are not also trusted. So, if you lock your design in highest level of abstraction, like in C, C++ or in the RTL, so even if they get some information, that is also kind of protect against those EDA tool vendor as well. Okay. So, this something give that benefit as well. So, and we will see in today's class that when you lock the design at the higher abstraction level, the things that I am going to lock versus whatever I am going to lock at the gate level design is bit different. Okay. And specifically in the higher abstraction level, you will have more semantic information, right. So, you know where is the loop, where is the branch, where is the condition, where is the operations, you have all those control informations at the higher abstraction level visible. But whenever you convert these things into a gate level design, you will not make out which is basically if else here, right, which is a which is the adder there, right. So, it is very difficult to get those semantic information at the net list or the gate level implementation. Okay. Whereas, whenever you are trying to lock it C, C++ or RTL, you have this semantic information, right. So, effectively if you go, so your synthesis goes this direction, right. You start with C, C++, you do high level synthesis, you will get the RTL, then you do logic synthesis, you will get the netlist, then you do physical synthesis, you will get the layouts and all, right. So, so more you go this way, you have more detailed circuit, but semantic information is missing, whereas if you do in higher abstraction level, you have more semantic information. So, we will see today that the kind of locking that you can do in the C, C++ or RTL, which is not applicable in the gate level design. So, this gives kind of certain other benefits as well. Okay. So, let us go into that. So, what are the kind of things we can obfuscate? So, effectively what you are doing, you are masking the behavior, right, or obfuscating the behavior from the user. So, what are the information which I can hide or obfuscate from the attacker? Okay. So, the one thing we can do is the constant, that suppose you are using 5 here. So, if you hide this 5, he will search for which constant this program will give the correct output, right. So, you just if you hide this information, the constant, say some information 5 here, and if it is a 32 bit, so now it has 2 to the 32 possibilities. So, he will basically search for which constant value this program is correct, right. So, this is one information we can hide. What else we can hide is the control flow, right. So, if this condition hold, then this is the operation, else I will do something else, right. So, now if I hide these conditions, right, if I can obfuscate this condition from the attacker, so he will not confident that it will go to the if branch or else branch, right. So, that will also give the corruptibility. Okay. So, now if you think about, there are k such if else block. So, the possible execution pattern is 2 to the power k, right. So, he will also search one of these 2 to the power k possibilities, the correct possibilities, right. So, you have to search for that. So, that is the information I can hide. What else I can hide? Let me ask you, there is no, it is just your intuition, right. What else I can hide from the attacker? It is basically he has to search for the information, the correct value, so that he can he get the correct version of the program. So, I told you that constant, I will show you how exactly we will do in the C level or RTL level or condition. What else I can hide here? C. Which C? So, basically, so you try to tell in the generic terms that constant, condition, what else? What else I can hide? Yeah, variable is one thing. So, or maybe the operation, right, operation itself, right. So, I am doing here a plus b, I could have done a minus b also, right, ai plus bi. So, I could have done ai minus bi also. So, if I do not tell them that which operation I am doing here, that information also can hide, right. Either so he has to now look for which operation will be applicable here, so that this behavior is exactly as the original behavior. And the last but the not least, the dependency, which is I think you try to mean by the variable, is basically the dependency, right. So, your Ci is coming here, this Ci if I use Ei, right. So, that is the variable you are talking about. So, that is the dependency, right. So, whether Ci is using here or Ei is using here, that also information I can also hide, right. So, this 4 information if I hide, that will be sufficiently difficult for the user to break it, and exactly the example that I have shown you on the bubble sort. I hide the constant in the bubble sort, start from I equal to 0. So, I just hide the 0, I hide one of the operations, and I hide the condition. The example that I have shown you there, I have exactly done these 3 things. Okay. So, let me see what we can do. It is very simple thing, right. There is no complex mathematics here, it is a very simple thing. So, suppose let us start with the constant obfuscation, right. So, you have Ci into some constant, say this is 5. So, it is happening like this, I want to hide this, and in RTL level you can also think that you have a adder, one of the input is Ci and that input is Cl. So, the same philosophy can be applicable at the C, C++ level as well as the RTL level, right, the similar analogy. So, how I can hide 5? Some idea? I will not let the attacker know this value is 5 in my design. What I can do here?
Use a pointer.
No, you think about a hardware terminology, right. So, it is although a C program, but it will be implemented in the hardware. If you store 5 in your some register, he can access it, right. So, I do not want to store 5, that is my idea. So, what should I do? Any idea? Yeah, so I will basically again bring key, right, but what I will do is very interesting. So, let us say I have 5, I do not want to store 5 in my hardware. Okay. So, what I will do? So, this is say 5 which is say 0 1 0 1, right, binary representation. Let us say I use the key which is say something say 4, this is my key. Okay. So, key is 4. So, 1 0 0 0. If you do a XOR of this, what will be the result? It is 1 0 0 0, right. So, in XOR if they are same, then it is 0, right. So, this is my 1, right, this is value is 1. So, what I will do in my design, I will store in my register this value, I will store 1 here, okay, and the key will come from. So, this is my design, right, key will come from outside, right, because key is basically coming from outside, which is not part of this. Then what I will do? I will use an XOR between this. So, the good part of is that if you do a XOR of 4 and 1, you will get 5, you do. So, this is 0 and 1, this is 1, 0 0 0, 0 1 1, 0 0 0. So, if I do an XOR of 4 and 1, I will get 5, and this value, this is XOR basically. This is an XOR, and then I am going to use this multiplier, where I am going to use this value and the Ci. This is Di. So, in hardware I will store the obfuscated value 1. So, user will think that 1 is the correct value, but it is actually the correct value 5, and if you do not give the correct key value, this will never be 5, right. So, it is effectively I make this as a variable, he has to guess this value, because this 1 does not help him, right. It is basically the 5 he needs the value 4, then only he will get 5. If he does not know the key is 4, he will not able to get the correct operation, right. This is exactly how I can hide constant, and this is exactly I have done in that particular example. Understood? Any question? This is exactly the I am talking about. So, you have this encoded constant, which is the one I talked about, this is my key 4, then I will get 5, and that I am going to use it, right. Make sense? So, now I will talk about control obfuscation, right. So, I do not want to tell the attacker whether you should go to this branch or this branch. Again, how can I do that? Some idea? So, this condition you can think about C, right. So, this checking is C, that if condition is con less than n, then this is 1, otherwise 0. I can think about that is a variable C. So, how can I hide? So, he will not able to determine whether I will go to the if branch or else branch. So, that is my idea. So, what should I do here? Some intuition? I am just saying ki condition you think about, this result is C. So, I will not touch the inside whatever it is, whatever is my C, I will try to play with that, you understand, right. So, basically you can think about C equal to cont less than n, and I am using here C. If C I will do this, else I will do the other part, but I will not let the attacker to go the correct branch, that is my objective. So, obviously, I will bring key, right. So, I have to bring key, otherwise I cannot control. So, what should I do here, so that attacker won't able to determine whether I should go to the if branch or else branch without the correct value of the key. Some intuition? Understand the question, right?
The same thing can be applied here because condition less than n is again a bit stream only.
Yeah.
You can again apply a key and get the.
Yeah. So, I am trying to say that it is kind of a Boolean value. Okay. So, I do not want to touch the cond or n, because n again you can hide, n again you can hide, n is a constant, right. So, you can hide that. So, it is a very simple thing. So, I have C, which is the value, I will just do XOR with, you can do many other way. I am not saying that what I am doing is the only way you can do, I am just showing one way of doing it, XOR with some k. So, this will be my condition now, right. So, basically if I will do now C XOR k, okay. So, I do not know whether it is a XOR is a smaller one, right, otherwise I will write XOR. Say, so suppose this operation is basically operation say OP1, I am just saying that, and this is why you are doing here OP2. Okay. So, I will put OP1 else OP2. Is it always correct? Everybody understand what I am doing? So, I was now doing whatever the actual condition C, I just XOR with a key, right. I am saying that whatever the if branch operation is OP1 and whatever the else branch is OP2. I am saying that if C XOR k, then you do these operations, else you do these operations. Is it always correct? How it will execute now? So, suppose if you assume that k value is 0, correct key value is 0, okay. Then this is C XOR 0 means what? What is C XOR 0? It is C, right, because if you XOR with 0, so whatever the value of C, that will be the output. So, if the value of k is 0, so it is effectively means C only, right. So, that means it is boils down to the original one. But what about if k equal to 1? So, if C XOR k if k equal to 1, then what will be the condition? It will reverse of C, right. If you remember XOR circuit 0 0 0 1 1 0 1 1. So, if the key is 0, so this is key, this is C. If it is 0, then whatever C, it is the output, right, 0 1 0 1. Whenever the key is 1, whatever the C value, it is opposite C bar. So, that means if the k is 1, I should do the else part, right. So, I should put OP2 here, the else operations I should put here, OP1 put here. Did you understand this? Yes. So, it is because you are locking, right. So, you know what is the correct value of key. Based on that, you decide whether I will put OP1 here, OP2 here, or OP2 in if branch and else branch. Everybody get this? Any question here? So, this is how I am going to lock, and if you only thing is that attacker does not know whether k is 0 or 1, right. So, if I keep this version, if he gives k equal to 0, then it is correct operation. If you give k equal to 1, then it will do the opposite operation, right. Same thing goes here, but the version I will choose this or this is my choice and based on the key value. Understood? So, this is what is basically the same thing, that you have this test C. So, I will not touch this one, I will touch the test, whether C is true or false, and there I will do this, right. So, I will basically add a XOR with key, and on that I will just do this, whether I will take the true branch or false branch, that depends on the value of key. Okay. Any question here? Okay. So, this is the same example, that if your key is 0, then the true and false will remain the same, right. If it is k equal to 1, then it will become false or true, right. So, your true block will come here, right. So, here true block is here and the true block is going here, because it will go to the opposite direction. So, the example that I talked about, this is just a pictorial representation of the same. Okay. So, so these are some techniques. So, now about operation obfuscation. I want to hide this operation. I do not want to tell whether you want to add or multiply between these two values, right. How can I do that? Again with key. Any suggestion that this is how you can lock this operation? Any suggestion? It is much simpler one. I just want to hide this information, that you whether you want to do addition or subtraction, I will not tell that occur, and that based on the key. If I give the correct key, then the correct operation will happen. If I give the wrong key, some wrong operation will happen. What should I do? It is basically you can think about that, say C I if k, then I will do A I plus B I, else I will do A I minus B I, right. What is the correct value of k here? What is the correct value of k? So, I am saying that if k, then you do this, else you do this 1, right. So, if it is here k equal to 1, if k equal to 0, then what I have to do? I have to just swap these two, right, k, then A I minus B I, else A I plus B I. So, here the k value is 0, because if k you do the wrong thing, else you do this, because k equal to 0, I will always do this, right. So, this is how I can hide the operation as well. Make sense? This is the basically the, if you do in RTL level. So, this is the actual operation, this is the fake operation, it can be anything, and based on the key value you decide whether you take this or that, right. This is how you can implement the same in RTL. Okay. So, this is easy to apply and just a marks, right, nothing else in hardware. And dependency is something, is the value is coming here, right. So, whether I will take C I or E I is the dependency, right. So, if I so if you do this, so this is your C I, this is A I, this is V I, this is C I, and this is happening. So, what I can do, I can basically add some fake operations and I will just multiplex between these two. So, it can be C I or maybe something else will come here. So, the dependency will change here, you got the point, right. So, it is similar to your operation obfuscation. So, I am doing here, this is your C I and this is something, say you are doing multiply, this may be D some E I, right, and whether I will select C I or E I, that is based on some key. If you give the correct key, then C I will come here, right. So, C I will come here, otherwise some other operation will come here, right. So, I can also touch the dependency as well. Okay. So, this is how you can actually lock this, and you can actually put it into an HLS and you get the RTL, right. So, if you do in the C level, in the C you can parse and you can implement all this 4 kind of obfuscation, and then you do the HLS, you get the RTL, right. So, you can do even starting even from C++ code, C++ code, or the same thing can be implemented in the RTL as well. Okay. So, just to demonstrate that, some design was taken. So, how many constant was locked, what is the key size, because you can think about that it is 32 bits, right. So, then 120 key size, this many constant was locked, this many branch was locked, this many DFG variance is basically the operation obfuscation, and finally, this is the key size. You can see here 400, 500, 4000 is the key size. So, just locking few constants, some branch, some operations, you can have a key size which is 800. So, if somebody have to apply a brute force approach, he will need 2 to the power 400 kind of trial to get the correct value, which is kind of infeasible, right. And overhead is less because you are effectively just, you see what I have done, I just add a marks somewhere, right. Operation obfuscation is marks, constant condition obfuscation is nothing but XOR gate, right. Constant obfuscation is also an XOR gate, nothing else, right. So, it is basically just adding one XOR gate or a multiplexers in your design, that is all. Or that DFG variant or the operation obfuscation, you probably had to have some fake operation that might increase your area. So, if you see here that this is, if this is the baseline, this control obfuscation almost has no overhead, then constant obfuscation also is very less overhead, but the DFG variant or the operation obfuscation has little bit overhead because you are adding some fake operations. But in general, the you can see the overhead is within 5-10%, right, which is acceptable, but that give you kind of a big protection against the entire IC supply chain. Okay. So, that is the kind of summary, and in the future work. So far what we have talked about, how do you lock. The point that I did not talk about is where to lock, right. So, it is not that if you arbitrarily lock your operations and constant, protection may not be always the same, right. If I use 100 bit, with 100 bit I can lock my design in 100 different ways, right. Not all of them are equal strong, okay. Not all the locking are equally strong. So, in the second half of today, I will talk about some attack technique, and it is not brute force. Nobody will apply brute force with 400, 500 keys, right. I will show you that you can actually use the theorem prover or SAT solver, and you can make an attack, and we can break those kind of circuits which has maybe have even 200, 300 gates. Okay. So, it is not something that you lock, I means you are very happy. Attacker will also try their intelligence, right. So, they are the intelligent person. So, formal way you can actually scale your attack to some 400, 500 keys also. So, the important point is that where to lock is a big question, right, and future research can be done on that direction, that with the same number of key bit, with the same overhead, which part of the design I should lock, that can give, it will be harder for the attacker to break the design. Okay. So, that can be a future direction of work. Okay. So, this is part 1 of this talk. I will now move on. Any question? So, this is I talked about in high level, right. So, now I will talk about on lower level. So, any questions? Is the idea clear that how do you lock in the higher abstraction level in C, C++, RTL? Okay. So, the idea is very simple, right. So, you just lock the constant, operation, conditions and all. Okay. So, now I will come to the lower level, right. So, I will try to do the logic locking, but these are on the combinational circuit or sequential circuit. Okay. And inside the combinational circuit you have different era. So, this SAT attack is one of the most powerful attack in the logic locking, which I will talk about in the second part of the talk. So, we can actually classify the I can classify the attack in basically two categories. The attack, the techniques which was used before SAT attack, and the technique that was developed post SAT attack. So, these are completely different attacks, different strategies. Also, we can actually lock the sequential part of the design. Okay. So, I will give you the brief ideas. So, I will not give very detail of the locking algorithms. I will just give you the intuition. I think that is the key to get the intuition in this kind of course. Okay. So, as I mentioned, so you have this. So, now I will talk about gate level design. So, there is no if else, no branch, anything, right. It is a flat gate level design. So, you cannot just say I will lock the if else, because you will not figure it out what is if else in the circuit, right. So, I have a flat gate level circuit, and I only interested in the combinational part, say for timing. So, I do not want to lock the registers, I do not want to lock the FSM, I just only want to get the gate level design get locked. Okay. So, you have a design like this. So, the idea here is that you after locking you will basically sell this to the market. The key is basically hidden inside in a tamper proof memory. So, this is basically a tamper proof memory. Okay. So, when you sell it to the market, user does not know what is key, right. It is basically packaged together. Only in the supply chain I will give this part of the design to everyone, right. I will basically do not give this value. So, they will not able to run the design with the correct key values. Okay. So, that is the my objective. Okay. So, your objective, as I mentioned, that you basically add some key gates. To introduce the key, you need to add some key gates, right. This is called key gates. Whenever you are talking about in the higher level of abstraction, so you just talked about this condition operations and all, but here because this is your circuit, right. So, this is your circuit, you to introduce another input you have to bring some gates, right. How otherwise you can add another input, right. So, these are the two inputs, right. If you think about this way, this is your design, this is your input, this is your output. Now, I want to lock this behavior, right. I want to obfuscate the behavior from the user. So, anywhere I want to lock, say suppose I want to lock, decided to lock here, what I will do, I will put some gate, let us say some XOR gate, and this is my K1, right. I want to lock this one, so I will put some gates, say X naught, I will put some other key. So, introduce any key, I need to add one more gate anywhere in the circuit. Okay. So, this is the way you have to do the combinational locking. Whether you want to add a gate or a multiplexer, whether it is a LUT, that is a design decision, but usually people use either XOR gate or XNOR gate. I can use multiplexer or I can use LUTs. Okay. So, if you use XOR gate, usually the key value is 0. If you use XNOR gate, usually key value is 1, because if I use K1 equal to 0, then this value will pass, right. And if you use K1 equal to 1, then XNOR gate, it will basically, if it is 1, then only it is pass the value. Okay. So, this is about the XOR XNOR gate. You might ask me that then just seeing the XOR value I can get the value, right. So, if I know that this is XOR gate, then K1 is 0, if it is XNOR gate is K2 equal to 1, then where is the locking? I just see the gate and I will tell you this is the value, right. So, people, the defender is not that full like me, right. I will told you how basically they hide that information. Just looking into XOR gate, you will not able to make whether the K value is 0 or 1, right. I will discuss that in few minutes. What is the concept of marks based locking? Is very simple. You think about that this value is going to this value, right. So, this input is going here. What I will do? I will basically remove this and I want to hide this information, right. So, what I will do? I will basically add a multiplexer here. This is one of the value, some other value, right. So, this is something other value somewhere from other circuit, and this is my key. What will happen if you think about this is 0 and this is 1, if you give the correct value, then only this value will go, right. If you give some wrong value, then some wrong value will propagate, right. And based on your key value is 0 or 1, you connect whether this will connect here or here, that will be determined by the correct key values. Okay. Similarly, LUT is also another way of looking into. So, which I can skip for the time, but this is the core idea, right. Either you utilize this XOR or XNOR gate or multiplexers. Okay. So, this is the overall idea of combinational locking. I will talk about various different techniques, but what are the design for security requirement, right. So, you are doing all those things, either you use XOR gate, XNOR gate or marks or all those things. what are the things you have to ensure? You have to ensure that no effect on the functionality, in the sense that if you give the correct key, it will 100% time it will give the correct output, right. So, that has to be ensured. And then the attack resistance. So, the way you have to do that, the reverse engineering cannot reveal the key bits, or it does not, basically design do not leak key during the manufacturing test, right. So, if you cannot pass the key somehow, basically you have to hide the keys from the attacker, right. Then you have to, so one question you should have been asked me that, sir, you want to do the test, right, of the design, after the manufacturing you do the test, right. So, we talked about the testing in the previous classes, all that. Now, if this locked design is given to the testing facility, and if I do not give the correct key to the test engineers, how they will test? Did you get my question? So, suppose this has been manufactured, right, and I do not want to give this key value to the test facility persons, then how they will test? They will not know what is the correct key value, right.
Temper proof memory can be given, sir?
No, I will not give. So, if I give, then they might tap this value and they can get it, right. So, what I will do? I will create some input output based on some wrong key, right. So, if I know that if 0 0 0, if the correct key is given, correct key, the output is say 1, right. If I give the wrong key, and the wrong key, say suppose correct key is 1 0 0, and I give say some one of the wrong key is 1 0, say 0 1 0, and the output is say 0. If it is say 0 0 0, so 0 0 1, so this is 1, so this is also 1. If it is 0 1 0, it may be 0, this is 1, this is 0 1 1, so this is 1, this is a 0. So, what I will do? I know this is the correct behavior, but the lock circuit correct behavior is this, corresponding to this wrong key. So, I will tell the test facility that you use wrong key is 0 1 0, and I will say that if this is the input, you consider this is the correct output of this lock design. In the manufacturing level, I do not need to check the functionality. I have to just check whether there is some stuck fault, some bridging fault and all those things, right. So that the desired output is coming or not, right. So, I do not need to check the functional correctness, I just want to check the structural correctness or manufacturing defects. If there is a stuck at 0 here, you will not get 0 at the output, because it is get stuck here, right, to 0. So, those kind of fault, the stuck at 0, stuck at 1 can be detected with a wrong key with this combination of values, right. This is my golden input output. So, this is how I can even pass the test process without giving the key, because I do not want to reveal the key to anybody in the supply chain, even to the user. It will be also packed in a tamper proof memory, so that even user does not know what is the key, right. For him is basically it is basically he will also give this input and output, right. So, he will only give the input to the design, he will get the output, he does not know what is the key here. Okay. Understood. So, this is what is very important, that manufacturing test can be performed without sharing the key. Okay. And this is that post silicon debug validation and all is basically the same process, we can do the same thing, and this should have less overhead, right. So, we have to just make sure that overhead is not too high. So, these are the kind of design for security requirement. Okay. So, now I will speak about few of the locking techniques. One of the first one came around 2012, which is called random logic locking, okay, or RLL. So, as the name suggests, you randomly pick a signal in the design, add either XOR gate or XNOR gate. So, this is how this is being done. So, so this is either XOR or XNOR, but you randomly pick the location, right. So, for example, if you think about this design, I decided to lock this signal and this signal. So, I decided that I will put this one equal to XNOR gate, that means this is 1, this is also XNOR gate, this is the key value is 1 and this value is 0, because I am putting XOR gate. So, what I will do? I will just put 3 gates here and I connect the keys. Okay. So, this you can do randomly any signal. Okay. So, there is no analysis that you should pick this signal or that signal, that will be better than this and all, right. Now, the question comes that if you give this any attacker, tell that your k 1 equal to 1, k 2 equal to 1, k 2 equal to 0 without any analysis, not running even a single test case, because the relation between the XOR gate with value and XNOR with the key value. Okay. So, how I can hide that information as well? What is the core idea? Did you remember that I talked about bubble pushing in one of the class? What was bubble pushing, you remember? You put two NOT gates somewhere, right, and you move them, right. If you there is an AND gate, if you put a move a NOT gate, it will become OR gate, right. The same logic will bring here, right. What I will do? So, I already have say I, so this one is a XOR gate. What I can do? I can put two NOT gates here, right. So, this become XNOR gate now, and this two NOT gate I can move here, right. So, I can basically put bubble around this XOR or XNOR gate and I move these bubbles, right, or the NOT gates. So, this is what is basically discussed here. So, I put one NOT gate here and one NOT gate here. So, this XOR become XNOR and there is one more NOT gate, and then I will pick this and this, I move here. So, I will get this design, right. So, this XNOR NAND become OR gate, right. This is the simple logic. Now, you see that, so still the k 1 value is 1, k 2 value is 1, k 3 value is 0, because I started from this design, but this is no more a XOR gate, this is no more a XNOR gate. So, the relation is broken, right. So, just looking into your XOR or XNOR gate, you will not able to guess what is the correct key values. Make sense? So, people will do that. So, they randomly pick the signal, put some XOR XNOR based on your idea that whether you will get select the value 1 or 0, then you just put bubbles, move them around, so that this XNOR and XNOR will get change, relation is broken, right. So, people will not make out whether that was a XNOR gate or XOR gate. Make sense? So, this is what is random logic locking. This is the first one proposed in this logic locking domain. So, this is the algorithm, but I do not need to go into detail. So, here you randomly select the gates and you put insert key gate, it may be XOR or XNOR, and then you do this bubble pushing here, right. This is the modification. So, you basically insert inverter and move them, that is all, right. Any question on this RLL? Understood, right. So, you can see the difference between that higher level locking versus this. So, there I lock constant conditions and all, here adding gates and basically modifying the circuit. Okay. So, one of the drawback, because the research moves on, right. So, whoever published, I think RLL is one of the most important work in this domain. They told that this is possible, right. This is how you can lock your circuit, but people later show that RLL is useless, right. So, next paper tell that this RLL is useless, you should do this. Then the next paper will tell that, oh, that your idea is also not good, you should do this, and this is how the research move on and the field becomes stronger, right. You get more robust solution. The same thing happen here. So, the criticism of RLL is that it does not take the impact of the key gate location on the output. Okay. So, what does it mean? So, as a result, RLL circuit may produce correct output even for incorrect key values. So, you cannot logically create a key which give you 100% corruptibility. So, here the term is corruptibility is very important. What is the corruptibility? If you give a wrong key, what is the chance that output will be wrong? So, that is corruptibility, right. So, if the design has a fair, here I have ABC is the input, what are the possible inputs? 2 to the power 3, 8, right. So, this is, it can be 0, 0, 0, 0, 0, 1 and so on. So, these are the possible inputs, right. So, this kind of analysis is possible for smaller design, but for bigger design is not possible. Then since you are using 3 key values, what are the possible values of the keys? Again 2 to the power 3 is 8, right, and let us say this is 0 to k 0 to k 7, this is 0 0 0, this is 0 0 1, this is 0 1 0 and this is 1 1 1, understood, right. If the circuit is small, you can actually create this truth table, right. So, if you give this value, what is the correct output? This is your correct output. So, this is the, for this input, the original circuit would have produced this output. For this input, this is the output and so on. Okay. Now, if you give k equal to 0 0 0, your correct value is k 6, right. So, 1 1 0, you remember. So, I have used 1 1 0 is the correct key value, right, 1 1 0. So, this is my correct key values. So, if you give the correct key value, no matter whatever the input, for which the output and locked circuit output will match, that is the function. If this is what the expectation. So, this and this will match, right. But if you see the other values, if it is k equal to 0 0 0, it is basically producing wrong output in 50% cases, right. 50% cases it is producing, wherever it is kind of white, that means the correct value, it is matching with the actual output, and whenever it is kind of red, it is wrong output, right, it is the opposite output. So, what I am saying here is that whenever I am giving, if somebody select that k equal to 0 0 0 wrong key, the corruptibility is 50%, understood. If you give 0 0 1, corruptibility is 3 out of 5, which is kind of 25%, 27%, right. So, this way you can make out that you do not have any key for which you get all output is wrong, right. It is not possible. Some cases it will cancel each other and you will get the correct output. Okay. Everybody understand this table, corruptibility. So, what will be your objective? When you select these keys, the number of red box will be more, right. So, one particular locking is better than the other if the number of red boxes in this table is more as compared to the number of white boxes. That means, you are making more corruption to the output, understood. But RLL does not talk about that, because it is RL, right, random logic locking, it just randomly pick the locations, right. So, the next research obviously try to bridge this gap, right. So, what they do is basically called fault analysis based locking, which is basically they say that if there is a fault here, what will be the impact, and then they try to generate the locations which basically create maximum corruptibility. Okay. So, so they do some analysis, so which I want to skip. So, it is basically impact of the fault. If there is a fault at that location, what is the total impact, and based on that they can calculate for each locations what is the total impact, and based on that the location which has the maximum impact, you will pick that, right. So, in this particular design, if you do this, you should pick the first, you should lock this one, right, that is by this calculation, and then you basically pick those locations and lock it. Okay. So, this obviously, because you do a specific analysis, it will give you a better corruptibility compared to random logic locking, understood. So, the next one is strong logic locking. So, what they talked about that in the fault analysis based logic locking, they try to put the key on sequence, right. So, they are not interfering each other. Okay. You can independently analyze and get the keys. Okay. So, strong logic locking actually bring that gap as well. So, what it does? It says that I will not put them in chain, rather I will put in parallel path, so that if you try to analyze this key, you need to consider this key value. If you want to try to find out this key value, you have to also consider k 2. So, they are not independent, right, because they are getting merged into the one output. Okay. So, this is what the basic idea of this pairwise security. So, try to find out how many such dependencies are there. So, it is basically saying that k 1 and k 3 is in the same path. So, K1 and K3. So, it is basically to get the value of K1 you need to also consider the value of K3. To get the value of K1 you also need to analyze the value of K2 and so on, right. So, this way they told that I try to lock somewhere that this kind of interfering is maximum, right. So, that you cannot analyze the one key independently without the other one. Okay. So, that is the idea of strong logic locking. Okay. So, this is basically maximize the number of pairwise security gates, right. And so, they try to make the maximum click with the dependency between the key gates. Okay. So, that is the idea. So, if you take the same design which I shown you, if I do the random logic, probably I will put these two key gates. If I probably do the fault attack based logic locking, then fault analysis based logic locking, I will put them into this way. This will give the best protection, and strong logic would have been given in this parallel, right. So, these are all 2 gates, but this is much harder to break. Okay. So, this is the kind of the progress in this particular domain. Okay. So, there are few more techniques are there, but as I mentioned all this technique was broken when the SAT attack was proposed in 2015. So, as I mentioned the first logic locking came around 2011, and then there are few more, right, strong logic, FLL, and there are few more are there, marks based logic, LUT based locking. So, those things came, but then this SAT attack came in 2015, and that told that no matter whatever logic you do, whether it is a strong logic locking, FLL, RLL, I can break them in minutes. Okay. So, that is the kind of motivation of this SAT attack. So, I will take a break now, and I will come back and I will say you lock, I will break. So, how can I break with the formal techniques, that I will start in the after the break. Thank you.